So we're continuing in chapter 8. And we talked last time about this picture here, which is using the MMU to create the actual physical address, right? The computer recognizes, the program is compiled to understand, let's say 346 is the address. And we can dynamically change that. This is a hardware instrument, so it's very quick, the MMU. And he'll change it, he'll add a 14,000 to it. So now the memory will be somewhere else, and we could therefore push off the location by any factor we want. And of course, this register here, this 15,000, will be loaded by whom? When will that be loaded and by whom? What? The OS. Yeah. The operating system, when it switches this program to start running, it'll set up this value. And it'll just set it once and leave it as long as the program is running until it's switched out and some other program starts running, and then it'll have to change it. And then when it switches this one back in again, it will reset it every time.
And between threads, it doesn't switch. This is between processes.
Right, because threads share the same memory space, so you wouldn't need to change it between threads. Yeah. Okay. Now we're talking about something else, dynamic loading. But the main function is loaded into memory. Other functions are not loaded from disk until they are called at runtime. So this is another idea. We can say like this: we can have functions in our program that we leave them on the disk, and we don't load them into memory right away until we need them, because there could be this a function we'll never use. So why bother copying its memory into our memory? Unused functions never loaded. All functions are kept on disks in a relocatable load format. There's in some format, the addresses of them are all relative, basically. They're not an absolute address. Useful when large amounts of code are needed to handle infrequently occurring cases, right? If you have a case, for example, some unusual error occurs in your program, you have a lot of functionality to deal with certain unusual errors. In fact, most of your program could be dealing with errors, and the actual main focus could be very short. So why load that into memory if you don't need it? That'll save memory. We can continue that idea and have something called dynamic linking, which is, so what is static linking, first of all? Static linking is that system libraries and the program code, which are, right, the system libraries is like if I do an include of IO stream and my program itself, these are combined, all that code is combined by the loader into a single binary program image. And that image is loaded into the computer. And now I have that whole library called IOStream in my program, and that's taking up memory. Dynamic linking is saying that that we won't link to that other section, that in other words, that other piece of code, that code that runs the library function, we won't link to it, we won't connect to it until we use it. So it's dynamic, it's run during running time. So how do we find it? So what we do is we put a small piece of code called a stub, is linked in before runtime. And then when the function is called, the stub locates the appropriate memory resident library file function, resident library function, and loads it. It loads it if it is not in memory. In other words, it could be that it's already in memory. Why would it already be in memory? By whom? By some other process. If it's a library function like IOStream, it could be already in memory. And I could just link to it. I don't necessarily have to have it in my code. We'll see how this is done in greater detail later. But the stub replaces itself with the address of the function and executes the function. The operating system will check if the routines processes memory address. If not in the address space, add to the address space. So that's a key point. If it's program code from another program, well, remember we set up, this is my memory, this is your memory, this is somebody else's memory. How am I able to use memory that's already been loaded for some other program? It's in his memory code. So we have to add the beginning and ending somehow. We'll have to add that location of wherever that function is, or that set of functions in memory is, and we'll say that's actually legally your memory space 2. So we're sort of having shared memory. We'll see how we're going to do that, but we're not really fully explaining it. This is useful for libraries, like we said. This is called a DLL, dynamically linked library. Now, the library is already in memory, but I link to it when I need it. It's also known as shared libraries. Consider applicability to patching a system libraries. For example, if a new version of the library is installed, the program does not need to be recompiled. Because here it was static. In the static meant I actually created one image of the program with that version that I did at the time that I compiled. Now at the compile time, I'm not doing anything. I'm just referring to it. So if I change the library, first of all, I just change it in one location. And secondly, now I'll just be using the new version without even having to change anything in my code. My stub will stay the same. Since we are sharing the code among different processes, the OS will have to determine that the process may share this memory space. Otherwise, we have a problem conflicting memory space. That's what I mentioned a little bit earlier in this slide, that you need to give permission to two different programs to use the same code. Yeah.
When we say that the stub replaces itself with the address of the function, is that just like a function pointer, or is that some other mechanism? It's possible. It sounds like when we say that it replaces itself with the address, that sounds like the function isn't in the code itself, it just references it from somewhere else.
Well, it's always right. It's the stub is going to take up less space than it, so it has to be a reference of some type.
Mm-hmm.
But with the point what we're trying to make here is there's two possibilities really. One is that it's already in memory, and the other is that's not. If it's not in memory, we'll load it, and if it is in memory, then we'll just refer to it. But even if it's not in memory, we can eventually refer to it. I don't think we can put it in a space. We don't have enough space for it.
Should we worry about like race conditions if we're dynamically linking the library? Because if we change it at maybe some other point.
Well,
then like
the library is going to be read only, so I'm not sure
Okay,
exactly.
fair enough.
Yeah.
Thank you.
Okay. Swapping, another concept here. We're kind of jumping from different concepts a little bit, but we'll sort of pull them all together in a continuation. So what is swapping? This is the idea that I have too many programs running on my computer, taking up memory, and I'm running low on memory. So I have two choices. Either I kill a process so that my computer will run at a reasonable speed, or the operating system itself can decide this process, I'm going to stop running it. I'm not going to kill it. I'll just freeze it, and I'll take it, but it's still in memory, still using. It's got some memory that it's using. I will copy out all the memory from the RAM to the hard drive. So this program is like been frozen and then moved away. And now I can reuse its space. That's the idea of swapping. Total physical memory space process can exceed. In such a system, I could actually have the possibility that the total physical memory of all the processes together is larger than the memory that I have. Because it could be half of my processes have been swapped out to the disk. So you understand that I'm using the disk instead of my memory, and what happens if the user all of a sudden clicks on this program and wants to start running it again?
You bring it back.
I'll bring it back, and then I'll put somebody else out maybe. That's called swapping. The backing store, which is the hard drive, has to be big enough to accommodate copies of all memory images for all users. It must provide direct access to the memory image. Right, you have to be able to directly get there. I don't know what indirectly would be, but fine. Roll out and roll in. Swapping done solely to grant priority. Lower priority processes swapped out, so higher priority can be loaded and executed. So there's such a thing. Rolling out and rolling in means I want to bring in a higher priority process from the disk, so I roll out a process. I roll them out to the disk and roll somebody in from the disk, so that I can run this other process. Now, the problem with swapping, there's one major problem with swapping, which is that the disk drive is slow. and copying things, copying a whole memory of a program to the disk drive all the time is gonna slow things down. And the more we have to copy, the slower it'll be. Now, the system has a ready queue of ready to run processes which have memory images on, which have memory images on disk. So that's like. That's like, I really wouldn't call it the ready queue. It's funny that it calls it the ready queue. It really, I would have wanted to say in RAM here. It's sometimes we call it the job queue. There's two different queues. We call one is the ready queue, which is things that are actually in memory, and the job queue includes everybody, includes all processes that are both in and out of memory. It doesn't say that here. I don't know why I didn't add that. But here it's saying it's like a ready queue, including everybody. And we usually call this the job queue. Does the swapped out process need to be swapped back into the same physical address? When you bring it back in, could we put it in a different location? Well, theoretically we could, because we have this relocation register. The MMU has the relocation register, we can move it to a different place. Of course, it depends on the binding. If the binding was a compile time, then we're stuck. We have to put it in a certain place. Consider pending IO to or from the process memory space. If we're reading something, if we're doing like a read of a huge amount of memory, if we moved it to a different location, that IO command might no longer be relevant. I'm not sure exactly what I was thinking when I wrote that or when I left that there. These are slides from the book, and sometimes I left it there and I wanted to leave it. Sometimes I'm not sure why I left that. Anyway, I'll skip that. Modified versions of swapping are found in many systems. Swapping is normally disabled. But then if you have a certain threshold, if a certain amount of memory is used, then you start enabling the swap. Here's a question. Why is it that we normally have swapping disabled? What do you mean slower? Because we'd rather not have to swap things because it'll slow down our system. So as long as we can, we're not going to just start swapping stuff. We're only going to swap if we absolutely have to. Started if the certain threshold is reached, and disabled once it goes beneath that threshold. So here you see a picture of the process. This is the hard drive. This is the user space. There's a potential RAM memory, and we put a process in and put a process out and bring it to process in. Context switch time, including swapping. If the next process to be put on the CPU is not in memory. So this is going back to this idea that we have a ready queue of all the processes. So if the ready queue is all the processes, now it's all of a sudden the turn of a process, but this process by chance is not in memory. So that's what we're saying here. If the next process, usually, like I said, it's usually called a job queue. If the next process is to be put on CPU are not in memory, you need to swap out a process and swap in the target process. Context switch time can be then very high. For example, if you have 100 megabytes process, as the process takes up 100 megabytes, swapping the hard disk with a transfer rate of 50 megabytes per second, then the swap out time, well, if it's 100 megabytes, it's going to take 2 seconds, right? It's going to take 2 seconds to bring it in.
Yeah.
So that's what they write here, 2 milliseconds, 2,000 milliseconds, which is 2 seconds. Plus the swap in of the same size process, let's say. So that's 4 seconds. That's a long time. Total context switch is 4 seconds. So we can reduce the size of memory swapping by knowing how much memory really is being used. In other words, maybe we could bring in not the whole program, but just part of the program. Maybe just part of the program is running right now. And maybe by the time we're going to do the next swap, we won't have advanced that far in the lines of the code. So we'll only copy it up, 1,000 blocks. And then in the time that we have, we'll finish 1,000 lines. And by that time, we'll anyway have to swap out. And then we'll bring in the next 1,000 lines. Can reduce the size of the memory swapped. Right, we said that. System calls to inform the operating system of memory use via request memory, release memory use. So these are some system calls. We don't have to know that. Other constraints as well, pending IO can't swap out as IO would occur to the wrong process. In other words, the IO doesn't necessarily know about the process. That's interesting. What is he gonna, why doesn't the IO, if it's directly copying to a location in memory, maybe. Then he wouldn't necessarily know which process it is. He's just saying, he just got a command, copy from this disk. Copy this file into this location. And then if it's another process, it could be problematic. Standard swapping is, I'm skipping this thing, wait. So here, or always transfer the IO to an operating system buffer. In other words, always put it in the operating system, which is always in memory. And then the operating system knows where, when the new process comes in, where he is. And then we'll copy it to the operating, to that particular process. So this is known as double buffering. You understand what it means? It means that instead of directly copying it to the memory of the program, I copy it to the operating system. And in the operating system, when the program moves its location, it knows where to copy it to. Instead of having the IO be somehow independent. Whatever, I'm not really explaining this so well, because it's not explained so well here. It's not, we're just sort of giving a general overview of it. Standard swapping not used in modern operating system, but modified version common swap only when free memory is extremely low. We said that already. In other words, we don't always do swapping.
My computer does a lot of swapping.
Yeah?
Yeah.
Maybe you have too much programs running.
Sorry, what would we do instead of swapping? Like either we swap the whole program or we.
Just buy more memory. Okay, now we're talking about a major topic here, which is memory allocation, and we're gonna discuss three basic types. Contiguous, which means all the memory of a program is in one spot. Hello, welcome. Amazing. Wait a second, I gotta stop the recording. Don't wanna record that. Pause. Pause. Okay, so we're at this major new topic, actually. Which is three different ways of allocating memory for your program, right? Your program needs memory to run. So the most obvious way we've really sort of been implying up until now is contiguous. There's two other ways which we'll talk about. So let's start with contiguous. Contiguous basically means I give him a beginning point, an end point, and I say that's all for you. As opposed to what would be non-contiguous? Saying, no, it's not contiguous. You got a piece over here, a piece over there, and a piece over there. So let's talk about contiguous. So we use the relocation register to protect users, process from each other and from changing operating system code and data, right? Because I want to always add that 14,000 in our example, add some number, and I'll only go to those memory locations, and I won't be able to get to other programs or to the operating system. The base register contains the value of the smallest physical address. So if it goes to 0, it's essentially like going to wherever the base register is. The limit register contains the largest offset. Each logical address must be less than the limit register. The MMU maps logical addresses dynamically to the physical address by adding the base register or what we call relocation register. On context switch, the new base register is loaded by the schedule into the MMU, right? Now, every time a new process comes in, we have to. כן, זה מפריע פה בכיתה.
זה מאוד מפריע. יש פינת עישון בצד השני.
Really, smoke is coming in?
Yeah, I can.
Smell, yeah, that's why I went to do yelling.
Let's see this. On the context switch, the new base register. So right, every time it's a context switch, you have to change the number that's in the MMU for the appropriate number for that program. This also allows the operating system to use more memory or less when needed. Right, why is that? Well, I guess because you could change where the programs are by changing the relocation register of them. And you could give yourself, if you're the operating system, you could give yourself more space. For example, device drivers may not be needed in the operating system all the time. I might remove a device driver and then I could give myself less space. The kernel code can then be what is called transient, which means not always resident. So some of the operating system itself could also be swapped out, I think is what we're saying. So here we have this picture which shows kind of very similar to what we saw before, but we have our limit register. The CPU creates a logical address. And as long as it's greater than the limit register. What does that mean? What's
As
the,
long as it's less than.
now as long as it's less than the limit register. The limit register is, let's say you have 1,000 lines of 1,000 pieces of memory for you. So your limit register will be 1,000. And if you try to go to place 900, so that's less than 1,000. So then you can go on. Now, once that's the address that he made, like he made address number 500. But really, it's 500 plus 14,000, wherever I'm relocating to. And then I'm going to that memory location. In other words, the actual place won't be determined till here, but we'll check already the theoretical place as the logical memory. We'll check that it's beneath the limit register.
So the limit register isn't like an actual place number, it's the amount of places after.
It's the amount of places, yeah. Exactly. We said that before also. When we originally talked about the base register and the limit register, we said that the base register is where you begin, and the limit register is how far you can go. It's not the end point, it's how far you can go.
Alright.
Okay. So each process allocated one or more partitions of memory. Questions like this: how do you allocate the memory? How do you decide how much memory to give a process? Well, you know the size of the program, but you don't necessarily know what dynamic allocations he's going to do. Maybe it'll be in the program. Let's say the program itself is 1,000 bytes, but in there's a command to make a new array of 10,000. So you maybe have to give them a little bit more than the actual code takes up, because you don't know what arrays they're going to make. So first of all, there's an idea of fixed size partitions, which would mean like we would take up all of our memory and divide it up into fixed sizes, and say like units of 100 megabytes, and every program gets 100 megabytes. That'd be kind of like a very basic way to do it, and just say everybody gets 100 megabytes, and that's
What if
it.
someone goes over?
So they can't. You can only run. That's it. Fixed degree of multi-programming is limited by the number of partitions. If you have 100 megabytes for everybody, and you have 1,000 megabytes, so you can only have 10 programs running. That's it. So that would be like a theoretical way of doing it.
Yeah.
Another way is a variable. The opposite is variable. For efficient size to given process needs. So okay, we try to figure out what it needs. The truth is, there's also theories. I mean, we don't really talk too much in this course about how you figure out how much it needs, but let's just say somehow you figure out how much it needs. Now, when you are trying to, that means that different programs will have different size blocks that they need, different size spaces that they need. And how are you going to decide where to put something? So in the beginning, you'll just put, like, for example, here's a picture. Let's see the picture. In the beginning, you put in process 5, then process 8, and then process 2. And that's the space you use, and that's what they need. Now, process 8, let's say, he goes out, he finishes. So now you have this space, and process 9 comes in, you'll obviously put him there, and you'll put 10 there. And then your hole will be this space here. Now, if process 8, all of a sudden, somebody runs it again, he has no space to go. Not only that, there could be other situations where, what if process 9 goes out? We'll talk about this. What if process 9 goes out? So now you have a space here and a space here. What if a new process comes in that needs this amount of space? He needs this plus this.
That's interrupted.
So since it's contiguous, it has to be contiguous, we can't give it to him, but we have the memory. So we have a weird situation here where we have the available memory, but we can't allocate it because he needs a bigger piece than the biggest piece we've got. And we can't combine two pieces.
We can't relocate process time.
So one idea would be relocate process 10, slide him down, and then make room for him. Yeah, you could do that. You could do that. You can do anything,
Or
remember?
don't you have to like, then you have to end it and start it again? Like, it's not gonna have any of the,
Exactly, you'd have to, well, you could just swap him out. You could wait for him, right, you would have to swap him out. And then when you swap him back in, you just swap him to a different place and put a different relocation register.
and by then, different process.
I mean,
And by then the new process.
relocating within memory is probably easier than swapping him out, because if swapping him out goes to the hard drive, but this you could just do within the memory.
But you'd have to copy all of these
Yeah.
memory locations down to here.
But that would be fast, that's still faster than swapping out, right? Swapping out is good to the hard drive.
Yeah, although. Yeah, it's a good, interesting question. We never discussed this in the course and I don't know the answer, which is how can the MMU copy from, generally the MMU copies from the disk drive to the memory. Can the MMU relocate one group of memory? Who's gonna do that job of copying those pieces? If it's the CPU, then it could take a long time.
Uh-huh.
If the MMU could do it, then it would certainly be fast. Okay, so we've defined already what a hole is. We have various holes. We have holes of various sizes that are scattered throughout the memory. When a process arrives, it is allocated memory from a large hole, from a hole large enough to accommodate it, right? You can't give it a hole that's too small. Processes, except if you, wait, we could though, in a certain sense. Because remember we said before that we have dynamically linked libraries or DLLs, we have dynamic allocation. We could put in some of the program and the rest not. We could with swapping. If we combine swapping with this, then we could fill our small holes. But we don't like to swap, like we said, and by default, we don't swap in the beginning. So we're not gonna. When a process arrives, it is allocated memory from, right? Process exiting freezes partition. Operating system has to maintain information, it has to have a list of all the partitions and who they're allocated to. And also all the partitions that are not allocated, all the sections that are not allocated. A list of holes, essentially. Now, once we have this idea of creating holes, we can now have fun with thinking about algorithms for allocating them. And we have three ideas here. One is first fit, which is saying like this. Let's say I have a bunch of holes and I'm trying to find one that fits 10, let's say. And then I have a hole that's 11, a hole that's 17, a hole that's 25. Where should I put it? I have three possible places. I put it 11, 17, or 25. It's only 10 that I need. So one is the first fit. The first place that I happen to come across in my list, I have a list of all the holes. I just go through the list and the first one I put there. The second idea is the best fit, which means that I've got to check all of them and check all the ones that are, let's say, anyone that's larger than larger or equal to the size that I need. So keep track of it. And then of those, get the smallest one, right? The smallest one that fits. And then there's another, which just makes sense because then I have like the least waste. I have the least waste. If I go to first fit, I might put him in like a big space that he doesn't really need. But maybe he will, I mean, he might, maybe he will need it. I don't really know. But at this point, assuming I know, he doesn't need it. The other idea is worst fit. Now, worst fit seems like a stupid idea. Why would you intentionally put it in the biggest hole? So the idea, what's the idea?
We put another process.
Exactly, produces the largest leftover hole. We want to leave, then if I put it in the biggest space, then that means likely that the small spaces won't get smaller. Because I could, for example, if I had a space of, let's say, 16 and I need 14, then I'm gonna have a space of 2 left over. And that 2, nobody's ever gonna really need, because it's so small, it's probably gonna, so if I keep on doing that, putting things in the best fit, I'm gonna end up with all these slivers all over memory that'll never be used. So this idea is try to avoid slivers. That's it, worst fit. But don't think worst fit is actually good. It tested it empirically and it's not really so.
Should you do a combination of them? Like
I
best,
think there was once a test question like that, yeah.
Yeah.
You could do anything.
Yeah, maybe it's like
Anything that
14
you
on
can
side.
think of, you could do.
does anyone do that? Sorry, that's a better question. Does any operating system work by?
Nobody uses contiguous allocation of memory, so it's pretty much.
So he's got it.
What?
It's so easy to think of.
Yeah.
Yeah, it could be
It's
good.
it's contiguous, easy to think about.
Very intuitive, there's a whole, put the thing in the hole, yeah.
Really, we're just learning contiguous so that we can understand. Is he still smoking up there? No?
They're not there.
Okay, good. The reason we learn contiguous is just so that we can understand it and then understand what we're gonna do next. It helps us understand what we're gonna do next. Okay,
Sure.
external the truth is what most people do is something we're not even gonna learn what most people do. Most operating systems do. Which is we're gonna learn is what's called paging, where there's a fixed size of pages. What most operating systems do is they have varying sizes of pages. Well, whatever, let's continue. External fragmentation, so what, once we've talked about these holes, we've introduced this idea, now we have this concept called fragmentation, and there's two kinds of fragmentation. One is called internal, one is called external. What is external fragmentation? External fragmentation is those slivers. Total memory space does exist to satisfy requests, but it's not contiguous. It's in lots of little partitions. Creating all those slivers, which is I've allocated to this program, this space, from here to here, and this one to there, and I have all these little spaces that are unusable. That would be called fragments, so fragmentation. Why do we call it external? Because it's external to the program. It's not, the program is not assigned it. Internal fragmentation would be if let's say I had a program that needed only 14, but I gave it 16 just in case, or because I had a hole of 16, so I'll give it the whole hole. So now he's got assigned to him 16, but he's only using maybe only 8. I misjudged. I thought he needed 14, or I thought he needed 16, and he's only using 8. So that's called internal fragmentation. Why internal? Because it has been assigned to a program. So it's internal to the program. But it's fragments, it's things that I can't use, that are unused.
So I don't understand when external fragmentation exists. Isn't every case where like everything is a whole and some things are assigned? So something be unassigned.
Well, I mean. The way they define it here on the board is by saying that. It's not called fragmentation, it's until I actually need those spaces, but I can't use them because they're spread out. In other words, fragmentation means that I've got a program here and another program here, and in between it, I have a fragment that's not assigned. So you can say, well, maybe you will assign it, so why is it fragmentation? So it's called fragmentation only when I have, a couple of holes. And I need something that needs the whole space, but I can't give it to it. So I have space, but because the space is fragmented, I can't use it. Yeah, exactly. That's just what I was talking about before.
And what's internal fragmentation?
Internal means that it's been assigned to the program. It's the memory to the program, but the program doesn't need it. It's like if I would give you an apartment, you're a young couple, you only have no children, and I give you an apartment with 4 bedrooms. So it's internal fragmentation, you have these rooms that you just don't need. Because why is it called fragmentation? Because it's unused. It's memory that's unused, but it's internal to the program. Why is it fragmentation? Because you said to me, I need an apartment with 1 bedroom. And I gave you one with 4 bedrooms, so.
Wi-Fi reconnected.
Was I muted all that time?
No,
Now what do I get?
I think I
Share.
just saw like the window pop up, so I think that just disconnected randomly.
Okay.
I don't know how much we lost, but
It's fine, it was all right. So. External fragmentation makes more sense to call it fragmentation. Internal fragmentation really should just be called internal stuff that's unused. Internal in the sense that it's internal to the program. You see, if in order to not have external fragmentation. I not have internal fragmentation, I would chop up the apartment and give you an apartment with only 1 bedroom. And then have 2 bedrooms left over. And then another person came inside, just need an apartment with 1 bedroom. And then I chopped up another apartment with 4 bedrooms, he only need 2 bedrooms. So I gave him 2 bedrooms. Now I got 2 apartments of 2 bedrooms and 2 bedrooms which don't have any kitchens at all, but they're not internally assigned to anybody. Now comes along somebody and says, I need an apartment with 4 bedrooms. Well, I've got 4 bedrooms, but I can't give it to them. Because they're separate on different floors.
Yeah, a fifth bedroom now with a kitchen and then bedroom.
But still, no, but they need 1 apartment.
Yeah.
So first fit analysis reveals that n blocks allocated. About half of them will be lost to fragmentation.
Half of the space? Or half of the blocks?
N blocks is when we say block, we mean blocks of memory.
Yeah.
So let's say a block of memory is, let's say, 10 kilobytes or
Right, so
whatever.
that means like 5 kilobytes are lost.
Wait, what does it mean? N blocks, let's say I have,
Above
5
kilobytes, and you
I have 5 block, I have 10 blocks, each one of 10 kilobytes,
So then
okay?
50 kilobytes are lost to fragmentation. That what it's saying?
So it's
Half of it. If I have,
Yeah.
yeah, if I have 100 blocks, then, sorry, if I have 100 kilobytes,
Yeah,
then 50 kilobytes will be lost, that's terrible, right?
it's not good.
A third may be unusable. I don't know what the 50% rule is, but whatever, so that's bad, first fit is not so good. They're all gonna be lost to, we're basically gonna have this problem of fragmentation, so what are the solutions to it? So one is something called compaction. Which means you shuffle the memory contents. To places all free memory, as you place all the memory, you push it all down to the bottom. And you make a big space at the top. But that, of course. Compaction is possible only if relocation is dynamic. In other words, if we have that relocation register. And anyway, we're doing it dynamically. See, once we built that system, that we have a relocation register and it's not assigned by the compiler. You are in this location, you are in that location. So now we can put them anywhere. So now we can do now we can do compaction. Execution time, which is execution time address binding. If done at compile time, we can't relocate. So the other problem with compaction, so the personal compaction requires that we're only using address binding that's dynamic. Second thing with compaction is obvious that it's going to be very slow.
Yeah.
You have to move everybody around. Another solution would be to allow a process memory to be non-contiguous and scattered throughout the memory. And that's what we're going to do. Consider that the backing store has the same fragmentation problems. In other words, if you store a file on the disk, you also probably want to put the file in one place and the next file in another place, the next file in another place. Now you delete this file and you have a space there. Now you want to store a big file, but you can't fit it in there and you can't fit it beneath. So you have the space, but you can't use it. So again, you have the same issue with files on the hard drive. So we have 2 solutions, and one is called segmentation, and the other is called paging. Memory management scheme that corresponds to the user's view of memory. But this is actually used by a lot of operating systems. A program is a collection of segments. A segment is a logical unit such as the main program, let's say a particular procedure or function or method, an object, maybe an array. The stack itself, the symbol table is what connects addresses to function names, I think. And then arrays, they're all different sections of your program. Now, instead of viewing your program as one thing, and I got to find a place for it, let's view it as lots of little things. And then those little things, I have a better chance of finding a place for them because they're themselves slivers. So I'll find a sliver for them. So the user's view of the program is that he's got all these logical addresses. And in there, he's got his stack and his symbol table, his program, his functions. Okay. Now what we'll do is we'll take that logical view and we'll map it to different places in memory. So you see that we'll put all the different sections in different places in memory.
So basically the same thing as contiguous, but just like smaller.
Yeah, except it's not contiguous now. Because now look at 1, 2, 1 and 2 are not contiguous. And there's a gap between 4 and 2. Right? They're not contiguous. They're not all in one spot. The program is now spread out throughout my computer, throughout my computer memory. So you could say it's the same as contiguous, so it's not contiguous. Adjacent, next to each other. You never heard the 48 contiguous states? The next people say the 48 contiguous states, because Hawaii is not touching another state, and Alaska is not touching another state. There's the 48 contiguous states that are all touching each other.
Yeah. From where we know.
There used to be only 48 states. And
Used to be,
what?
used to be 13 states.
It used to be 13.
What are they contiguous?
Well, they didn't used
Were
to.
they contiguous?
Well, here's it. During the Civil War, how many states were there? Did you, once the secede, would you count them?
We should do a sneak more and see what happens.
I should give you
Did they ever
a.
consider them, did the United States
Do you-
federal government consider them no longer states?
No, they consider them states. They're still states. Did you know that, but which new state was created because of the, during the Civil War?
So West Virginia,
West Virginia.
see from Virginia.
Because seceded from, Virginia seceded from it, really. It should really be called Virginia, and West Virginia should, and Virginia should be called
East Virginia.
East Virginia, because it remained in a state. But yeah, I don't know who seceded from who, but yes. And did you know that the Emancipation Proclamation, when he emancipated the slaves, he didn't actually emancipate the slaves? I told you this before, or?
Oh, no.
He didn't actually emancipate the slaves. What he did was he emancipated slaves in rebel territory. Which meant that the slaves in West Virginia were not emancipated. And I think also in another state, maybe Tennessee, I don't remember. There's one other state that, or maybe Tennessee did, I don't remember, there's one other like quasi southern state that didn't actually secede.
Maryland?
There's also technically only 46 states.
What?
There's only 46 states,
Only 46 states,
because there's 4 commonwealths.
which are the four common,
Pennsylvania,
really?
I can't remember them off the top of my head, but yeah, there are 4
I mean.
commonwealths.
Ah, yeah, Pennsylvania is a commonwealth on a state?
Yeah, like when they're called to court, it's you'll say like the state of Maryland, it's the Commonwealth of Virginia.
Uh-huh, okay. Whatever the Commonwealth is. Cool. But Commonwealth sounds like communism. All the wealth is common.
That's dangerous.
Oh,
Wow. It was time in history when they were all states.
Okay, logical address. So wait a second, how are we going to get, wait, guys, back to the segments, how are we going to find the address? Remember, the CPU just creates an address, says, go to address space FF, A, B, C. So that's the address. It just says, I want this address. How are we going to know whether to go to here or there? If we had a relocation register, we just add a number to it, but we can't do that now. Why can't we do that now?
Because it's all over the place.
Because what number are you gonna add? If it's here, you have to add one number, and if it's here, you have to add a different number. And here 4, you'll have to add a special number, because it's not after 1. So you'll have to have all these different relocation registers, and that's not gonna be practical. You're not gonna have all these, because you don't even know how many sections you're gonna have. So what are we gonna do? We have to have something called a segment table. First of all, the logical address, even though we talked about it as a single number, we're gonna divide it up into 2 parts. In other words, it's like if we had a number, think of a regular decimal number, like you have 100, like let's say you have 1114. So it's 1114, right? 1114. So you can say it's a single number, it's 1114, or you can say I'm gonna view it as 11 and 14. I'm gonna view it as 2 numbers. The 11 symbolizes like something and the 14 symbolizes something. But the address is still called that number. So that's what we're saying. The address consists of a segment number and an offset. Which means like this. The first part of the number is which segment I'm in. It's saying like, am I in segment 1 or 2 or 3 or 4? And then the offset, the second part of the address, indicates to me where in that section I am. Yeah, okay, so,
How do we know where that is?
well, let's go through this order here. Segment table maps 2-dimensional physical address. Maps 2-dimensional physical address, I guess it's 2-dimensional, these two. These are, the segment table maps this segment to a 2-dimensional physical address. Each table entry has a base and a limit. Contains the starting physical address where the segment resides in memory and specifies the length of the segment. So we'll have actually our same thing that we talked about, actually, the base and limit registers, except they're not registers anymore. We're gonna have a base and limit, basically, we're gonna have a base and limit register for 1, a base and limit register for 2, for 4, for 2, and for 3. We're gonna say where they start and how long they are. But we don't have, we're not gonna put it in hardware because we don't have enough hardware for that. We're gonna put it in memory. The operating system is gonna store it in memory. So that means anytime I wanna go somewhere, I'm gonna have to go to another place to first find out where I wanna go.
This sounds very slow.
It's gonna be slow. Now, every memory read is gonna require 2 memory reads. Because I can't just, I don't know where I wanna go. I first have to read a memory location which tells me where is segment 1, where is segment 3? And that's itself in memory. So I have a memory read just to find out where I wanna go, and then a second, when I finally know where I wanna go, then I have the actual memory.
Isn't that like affecting?
So that's gonna
time?
double the time, since memory reads are the slowest thing that we
Yeah.
do, it's gonna double down, it's gonna double on this time of every, and not only every memory read, every,
Right, well,
every time we want to
Read the instructions.
read any instruction, every time we go from one instruction to the next, to the next, to the next, every time we have to do another read.
and also rights.
Everything we're gonna do, everything we're gonna do is gonna be a memory read. It's gonna be 2 memory reads. Okay, so
This is like that.
segment table, we'll have to figure out a way to improve upon that.
Yeah.
How are we gonna improve on that? What would you guess? From your course in Mivnei Machshev, computer architecture? How would you guess we would solve that problem?
Special hardware.
What? Cache.
Oh.
Exactly, cache.
It's true.
Well, we don't have registers, we're not gonna make the hardware do it, but we'll have cache. And we'll cache the table. So it would we'll cache the table, so at least one of our memory reads will be to cache, which will be much faster.
It's still pretty slow, right?
No, cache can.
Well, someone got double down. Well, before it was double.
Yeah. Big improvements.
And then it goes double.
So wait a second, so until we talk about, I didn't talk about cache yet really, but imagine I didn't mention anything about cache. So still we have this segment table, which has a whole list of base and limit registers in it, of all the different segments. I need to know where it is. The operating system needs to know where it is, because it's got a different one for each program. So we need a segment table base register. When we start running a program, we're gonna put into our relocation register, instead of using it for the relocation for where the contiguous memory is, we're gonna use it now for where our table is. If it's not in cache, assuming it's not in cache. We're gonna put, and that's gonna be the STBR. In other words, the segment table based register, it's a register. So it's an actual hardware register that will put where the segment table begins, and another register which tells us the number, indicates the number of segments used by a program. The total number of segments, because there's gonna be a row, there's gonna be rows there, and there'll be fixed lengths. Where the segment, because remember the table is a set of just a mapping, where each segment begins. So it'll be, we know how long the rows are, so we'll just say how many segments are used, and there's how many rows there are in this thing. Segment number S is legal if it's less than the SLRS, right, segment number. Right, it has to be less than a little bit. Okay. Protection. With each entry in the segment table, we'll associate also a valid bit to tell you that the segment might be illegal. In other words, because, well, it could be that I've already removed that segment. Why would it? I'm not exactly sure why we need this valid bit right now. I'll have to think about that. But we have a valid bit to tell me that the segment is illegal. Read, write, execute privileges will also tell us whether this segment can be written to, right? If it's code, you can't write to it. You can read from it, but if it's actual code, you can't write to it. The programs don't write to their own code. Not yet. Once we start allowing AI or ChatGPT to, write, can you ask ChatGPT to write a program and run it?
You can.
Sometimes you can.
You can't really run program.
No, it-
doesn't
it's
really
not-
run it.
Run it, it'll just give you that.
Yeah, yes, you estimated out.
No, but can you tell it, can you ask it to,
There are other ones that do. I don't think GPT-4 does.
It can't
So I'm
really, it can't really
What?
think it can't really process it like that. It'll tell you what the expected
No,
Output
you
would
tell it
be-
to create a file on my hard drive, which is the following program that does this.
That,
And
no, yeah.
then,
No.
once it's on my hard drive, run it. No, I don't think so.
Yeah, no, that,
Maybe
definitely
like the Windows one can, I'm not sure.
not. Mobile cannot.
I have to get it.
GPT
I don't think
has
so.
extensions that can do that.
Would you?
To create a
Yeah,
file. on your
really?
hard drive?
Yeah, it has a
Cool.
file system that you can access.
Really?
Yeah,
It can, I think,
Because then you eventually end up with a program writing itself.
I think,
Run the
Allowing-
AI program, and then it runs
AI
itself and asks you, what would you like to run? It goes, run the program. And
allowing AI to write and run a program on your computer seems like a really bad idea.
Well, that's.
Welcome to the future.
That's not quality, it runs in on its own systems, there's the.
Okay, it's fine, oh, it's the.
Alright, let's go on, let's go on, so we have protection bits associated with the segment, code sharing occurs at the segment level, what does that mean? When did code sharing, when do we code share, when we're using a library function? So we could have instead of, I could share between, well, there's two programs could share a certain section of code, because they're sharing a segment. They don't have to share the whole code of the program, they could share a segment. Since segments vary in length, memory allocation is a dynamic storage allocation problem. In other words, we still have our same problem of. The way I understand what it means, is we still have our same problem of, what's it called? Fragmentation. Cause we don't know what we're gonna need, also, we don't know how much to allocate. Dynamic storage allocation problem, we don't know how much we're gonna need to allocate for each segment. Maybe all of a sudden he just says he does a declare and he wants an array of whatever the user tells him, and the user tells him 1,000,000, so now he needs 1,000,000 bytes. A segmentation example is shown in the following diagram. So what do we have here? This is our segment table. Okay, this is the address. The CPU just produces an address. It says read address number, FFAA. It just says I want address FFA. The hardware is going to interpret this in a special way. Or the operating system. The operating system interprets special way. It's going to take the FF and say that is which segment I want. That's the F, that's the S. S stands for segment. Which segment I want. So if he wrote, let's say, 3 in the S section, in the bits. Remember, this is bits. This is, let's say, 4 bits. I mean, it's normally more like 32 bits. In computer architecture, it was 32 bits. Nowadays, it's 64 bits. But let's take a simple example. Let's say it's 2 bits. So S is 2 bits and D is 2 bits. So this could be, for example, the value 2, 0, which is 1, 0. So he goes here and he goes down, doesn't go to 0, he doesn't go to 0, 1, he goes to 1, 0, and he gets to this line here, this row here. And then that tells him that the limit, that the amount that is allowed to go within that segment is, let's say, 10 lines. That's it, he's got 10 lines in that segment. That segment has 10 lines. That's the limit. So he checks what's the D. The D is the offset. The other 2 bits is how far I want to go in that segment. So if I want to go to segment to a place 11, I can't. If D is, well, D can't be 11 if it's only 2 bits, but let's say D is more than 2 bits. So then if I want to go to line 11, the limit register here will tell me to reject that request. But if this number is less than 10, so then it's fine. And then I'll go here and I'll say, take the base register, which is telling me actually where is this segment located? Because he said, I want segment, what did he say, 2? So segment 2 is located at whatever is written in base. Take that base and add to it the D that you got. Because the base is just telling me where it starts. And the D is the offset within that point. And it's how much from the beginning. Offset literally is, it's like how far you are set off from the beginning. That's why it's called offset. It's how far you are set off from the beginning. So. What?
I was there, it's symbolized by D.
So we call it D.
Offset.
The offset, I don't know, D, it's always called D. D, yeah, I think it's like the delta, maybe. Maybe that's why it's called D. No, delta, like delta, the difference
Right.
is the Greek letter in math for difference. Triangle, so I think maybe that's why, but it's a delta, how much from the beginning, I wanna go, and that, I'll add it, and then I got the physical memory. The physical memory now, I just read it. If I look at, from this perspective, when I go here, I'm like basically at the thing that says, the thing that's the memory reader. And he just gets a number now, and he just reads that number. But that number was the same D that the CPU produced, but with a different S. The S changed from being how many rows to go, to being whatever this, to being whatever this base is. So again, if the S was 2, the base might be 1. So then it'll be, but the 1 won't really be a 1, what will it really be? It's not like we're adding 1 to his 9 over here.
It's the base of
Because it's
the,
1, but it's 100. It's 1, but it's pushed over a certain number of spaces.
Okay.
Right?
So
In other
there's
words,
really
but
no
remember, the S is over on the left side, so that means it's a higher order number. You know what I mean? If this would be the number 1114, this is not 11, this is 1100. So when we get a number over here, let's say we change it from 11 to 6, it's not 6. We're not gonna add 6 to the D. We're gonna add 600 to the D,
I don't know.
because it maintains its location. You understand what I'm saying? No, where's my marker?
Oh, you're saying within the segment. Okay.
Number is just a number in the array, and the base is an actual hardware.
Here.
Space.
Let's say the CPU produces this number. What location is this? This is 1117. Now, that's the way, that's the CPU wants that memory place. But we're gonna trick it. We're gonna take this and say, no, let's chop it up into 2 parts. And the D we won't touch. But the S, we're gonna change whatever the base, whatever is written in that table. So we're gonna change this number to, well, let's say at this line over here is written the number 9. So it's gonna be, and we have a plus over here. This plus does not mean take 9 and add it to 17 and get 26 and go to memory location 26. That's not what it means. Because what it means is, or I mean, you could say it means that, but then the 9 wouldn't be a 9, it would be whatever. What it really is gonna do is gonna say like this. That 9 is really a 9 over here, and we're gonna concatenate it with the D. So it becomes 917.
So this is just how it works.
Yeah, I'm just saying it's gonna be more like, because it's bits. We're gonna take bits here. These are bits. These are 4 bits or 2 bits, or however many bits it is. Let's say it's 2 bits. And we're gonna replace it with these 2 bits. So it's gonna concatenate. I mean, they just wrote a plus here because, you know, you could think of it as plus. If you would write, instead of writing 9 here, you wrote 900, then you could do plus. But you're not gonna, why would you write 900 here? Because you know whatever number here is gonna have to be hundreds. Because if it's replacing this, if it's always 2 digits and 2 digits, then whatever number is in the base is always up in the hundreds column.
Because if it's dynamically sized or like segments, you don't know how big it's gonna be. It could be that the base is 900, or could be the base is 9,000, or it could actually be just 9 because it's a really small segment.
No, but no, because. Oh, I see what you're saying. You're right, but I'm assuming that this line is fixed.
Yeah.
If this line is fixed, then that means that there's a certain number of bits over here that's fixed. So that means that you're right, if the segments are different sizes, then this wouldn't be fixed. You see what I'm saying? Because this is how much within it. If it's different sizes, then this D could be different. Then sometimes this D could be 100 bits, and sometimes it could only 2 bits. It's right. It's a little bit confusing. I'm sort of assuming that it's fixed, but you're right. It could be that it's not fixed, and then it could get more complicated. But I'm keeping it as fixed. But you're right. Since it's not fixed, it doesn't. All right. Page. So now we're gonna go on. That's segmentation.
Are we gonna break here for a minute?
Yeah.
Oh, yes, definitely.
How the college students learn.
You're right.
I've been watching Code Consensus.
Anyway, I think that, yeah, I think there's a certain lightheartedness of 1960s cartoon, of the TV shows that were just. You can't get too riled up about anything if you're.
Brady Bunch. So just watch Brady Bunch.
Oh, it's Green Acres. You ever watch, I should stop this. Okay. So now we're on to paging. Paging is very similar to segments, but the basic difference is exactly what Eyal was asking me about, which is that the pages are fixed size, where the segments are not fixed size. So what I was telling you about how the plus and everything is a little bit more precise here. Paging says like this. Well, here, let me show you a picture. I always good to see the picture first. Here's just a basic picture. You have the logical memory of the program. You don't care about segments. You don't care, this is the main program, this is a function, this is an array. You don't care what you're dealing with, what the actual things are. You just say, I'm gonna take my whole program as a whole thing and chop it up into pages. Now the page size is fixed. So on the, let's say, the page size is 512 kilobytes. A half a megabyte. 512 kilobytes. So that's 512, 512, 512, 512. That's my program. Now I have something called a page table, which is similar to the segment table, where I say, well, page 0, I go to row 0 in the page table. The page 0 tells me go to row 0, and I see a 1 over there. And that tells me that page 0 is in the actual physical memory, the actual memory in location 1. Because I've also taken the physical memory and chopped it up theoretically. I haven't physically chopped it, but I've divided it in my logical accessing it into pages. So that the whole memory is divided into sections of 512, for example, kilobytes. 512, 512, 512. And so therefore, what this is saying is my program takes 4 pages. Here are my 4 pages. And it's from 0, whatever. These are all the pages. When I want to go to any address that's in this location, I'm going to take a look at this page table, and it's going to tell me, go to this page. Then when I want to go to something, any address that's logically, it should be in page 1. So I'm going to say, oh, go to 4. So I'm going to go down to here. I'm going to go to page 4. So I'm going to basically do adjustments of all the addresses. And it's going to be in units always of 512. So that actually makes it sort of easy, because if I want to know where this page is, if I see a 4 over here, I just multiply 4 by 512, and I know the actual address. Right? If I see a 4 here, 4 times 512 will mean that the 0, I have to add to it 2048. So this is what it is. 1, 2, there's 1,000, 2,000. So here's 2048 right at 4. So that's exactly what I did. So I just can multiply as long as the pages are the same. Now, what makes it a little bit more complicated, which we're not actually going to learn, but the way real operating systems work is that the pages are not all the same sizes. And then it gets more complicated.
They're not just segmenting?
No, you'll have, let's say, what?
They're not just segmenting?
What's the difference?
No, because there'll still be fixed sizes, but there'll be a set of fixed
Varying
sizes.
6 fixed sizes.
Exactly. You'll have like, some pages will be 4 megabytes. Some pages will be 1 megabyte. Some pages will be a half a megabyte. Maybe most of the pages will be 1 megabyte, you know what I mean? There'll be different size pages that maybe you'll have to indicate. I'm not sure how they exactly work, whether they have a limit on how many large pages there are. There's a certain number and it's fixed, or it could be that you just have to say, what kind of page is this? Is this a page, a large page, a medium page, or a small page? So there are, we're not going to learn that because, once you get the basic idea of pages, you understood the concept. You don't need to, so fine, you could have theoretically different size pages, but let's assume that we're going to learn that they're all the same. So let me go back. That was a peek ahead to give you an idea of what we're talking about, but now I got to go.
Not the variable sized pages, but these pages, are these pages correlated to the pages that we have in the hard drive?
Yeah, oh, in the hard drive, no, that's something else.
Those page sizes are not related?
No, usually they're different sizes. Those are actually not called pages, those are called blocks. Oh, no, sorry, I take it back. They could be the same size. No, I'm taking it back. Blocks are smaller. Take it back, yeah, they're independent, they could be the same size, they don't have to be.
Okay, not.
They probably are the same size, actually, you're right, but we didn't talk about, we talked about swapping, we didn't talk about pages in a hard drive.
So we talked about them, moving it in a computer architecture.
Did we? No, we didn't.
I don't-
No, we didn't.
Maybe we mentioned it one point, but
In computer architecture, we talked about blocks
I think maybe when we're talking about from cache, if they're a different size.
Exactly.
One page.
between cache. We talked about pages between, we talked about block size, it was not called pages, it was called blocks, and it was between cache and memory. Now, we're taking that same idea of cache and memory and saying between memory and memory. And it's between logical memory and actual memory.
I like how you do
I
that.
thought we had said that we had cache to memory, and then the blocks are the same size, and we have pages and we have files.
Oh, we mentioned, yes, and that one slide you're talking about, yes.
Yeah.
There is one slide where we do
What?
mention that there's a hierarchy, and then we talk about pages there, but
So
we never,
those pages, those
we never did any exercises.
No.
I like that it's got like pages and words and you're trying to have blocks in the middle. What is that?
Blocks are smaller than pages.
You have pages and you have words, like those words work well
Right.
together.
Why would a group
You have
of
many
us-
words on a page, then you should really have blocks.
There's no paragraph.
Yeah, blocks should be paragraphs.
Okay, whatever, but the size is like this, you have a word, which is usually 32 or 64.
Yeah.
And then you have blocks. And then the blocks make up a page. That's basically, that's the size. So these are the pages that we mentioned yes, these are the pages that we mentioned in computer architecture. But we didn't really talk about them much, because we were only dealing with
No, I'm
the
just curious
computer
if that's the same
itself.
size.
The hard drive is really not part, from the perspective of computer architecture, the hard drive is not even in the picture.
Right.
It's just memory and cache. There is no hard drive, everything is in memory. Here, we're actually, well, here it's also just memory, but we're talking about. Where there's where we're paging the memory, we didn't page the memory, well, whatever, maybe it is similar, okay, I have to think about it. Okay, let me go back to the beginning here, paging. So we're going, if we're going to, physical address space of a process can be non-contiguous now. Remember that picture we just saw? You don't have to have all your pages next to each other, they're non-contiguous. Process is allocated physical memory whenever the latter is available. We could actually give it one page at the beginning. And as it needs more pages, start giving it more pages. We don't have to give it all of its pages that it's ever gonna need right at the beginning. Avoids external fragmentation. We're never gonna have external fragmentation because by definition, there'll be no small slivers. All slivers will be page sizes. And every page size is allocatable. Somebody could get it. So there'll be no slivers. So we have no external fragmentation. Because we don't have variance, we don't have variant size memory chunks, they're all fixed sizes. I mean, like, with the proviso that they could be different fixed sizes. But even that will be okay, because they'll be in units of multiples of 2.
Mhm.
No, the worst case we'll have is that we can't allocate a large page, but we can always allocate a small page. Divide the physical memory into fixed size blocks called frames, so we use 2 terms, pages and frames. Usually, what we mean when we say frame is how it actually is in physical memory, and the page is how we look at it from a logical perspective.
What is the most common?
In other words, when in this picture over here, where it says frame, where it says page here, really, it's a frame number, and it says page. What it means is like this. This is the memory. The physical memory is divided into 8 pages, into 8 frames. And this page, page 0, is sitting in frame 1.
Frame is just the location of the page.
They're the same size. The frame is the location where you can slip in different pages in as you like. You can almost think about it as like a clear plastic frame where you can slide in a picture or a page. So the frames are fixed.
Because it's really like, there's things from the clear.
No, I mean like a hard frame, and then you slip in different pages that you want. So the frames are how we divide up the memory, but the point is the page and the frame are the same size. Let's go back. Divide logical memory into blocks of same size called pages. Keep track of all 3 frames. Now we're gonna have to keep track of all 3 frames so that we know what we can allocate and what we can't allocate. We have to know we have to have a list of all the frames for each, process, and that's our page table. To run a program of size n pages, you need to find n free frames and load the program. Set up a page table to translate the logical to physical address. Right, that's what we saw in the picture. Backing store likewise split into pages. What we mean to say that the hard drive will also be in pages, that was your question. The hard drive will also be in pages. For ease, that way we can swap out a page to the hard drive and then bring it back in. Really, it's just for ease. Still have internal fragmentation. Why? Now we have internal fragmentation even more than we did before. Before we had internal fragmentation because we may have just allocated it more because we thought maybe there'll be a new coming up and there'll be some kind of memory request. But now we're gonna have, by definition, fragmentation. Why?
The end of the.
Because let's say a program needs 1.1 pages. So he's gonna have to get 2 pages, can't get 1.1
That's
pages.
what we have varying fixed size. Program is allowed
Well,
to have-
no, you could do everything with just small pages, then you never would need larger ones.
That's cool.
We'll see, there are reasons why we want large ones. We want large ones particularly for the operating system itself.
A program
That's
is-
why we want large ones.
The operating system itself.
The operating system itself sometimes needs to have a very large array. I mean, I'll see, we'll talk about it. We talk about the page table. Where do you store the page table? I'll
A program is
remind you.
allowed to take more than one page.
What?
We split the program into components, and each one can take at most one page. But something,
We pitch what into
a
components?
program is allowed to have more than one page assigned to it.
Of course, look at, this is the example that we saw here. Look at the example I showed you. This is a program.
But these are all different components of the program, right? Like a single.
No. Instead of having segments where we divide it up into components, we just take all the program as memory and look at it and don't look in the internal workings of it and just chop it up into arbitrary locations. Speaking of chopping it up in the Middle East, you know why? I just understood now why, they always said that they just cut up these countries. They made Syria after World War I. And the borders are kind of arbitrary because they don't divide it up according to like tribes or religion. But they do, there is a sense to it. What they did is they divided up into make each country viable. For example, Syria has a little bit of seashore. Secondly, it has a little bit of Turkey. It has a little bit of the mountains in the north, so that it has water supply. In other words, they gave a little bit of the Euphrates River, so it has water. In other words, they made the country so that they would each be independently viable. Anyway, that's just a side point.
Also, the corner of the rivers.
Has some corner of the river, right? What?
I'm saying the Yarmouk and the Rukad, like
And
that.
Jordan doesn't really have much, because Jordan is really supposed to be part of Israel. Jordan doesn't have much of a, it has a very tiny little bit of sea coast. It has almost no water. As it's really supposed to be part of Israel. But blame it on Churchill.
So Churchill goes.
Churchill divided it up.
Right.
Churchill-
Transferred.
He made the transfer. Okay, so we understood pages, but let's now talk about what I was sort of mentioning before. This taking the address generated by a CPU is divided into 2 parts. So in other words, we take an address, let's say a 32-bit address. And we say we have a P section and a D section. The D section is the offset, the delta, and the P section is the page section. And what's the idea? The idea is like this. Let's say that our pages, let's start with some numbers. Let's say our pages are 512 bytes. Let's just say bytes. 512 bytes. What's the largest value? 512 bytes, 511. Right? There's the last byte would be, the first byte would be 0, and the last byte in the delta, in the D. This D would go from a range of 0 to 511. How do you represent 511 in binary? How many ones? 9. Very good, 9. We agree, it's 9, because you can remember it easily because 1024 is 10, right? 1 kilobyte is 10 bits. So 9, so if our pages are in fact 512,
Yeah.
if our pages are in fact, help me finish the sentence. If our pages are in fact 512, what? Bytes, then how big is D? How many digits of binary numbers are here? How many ones are here? 9. So if our D, so we've already, if our page size is 512, then D is 9 bits.
Yeah.
And if our whole address is 32 bits, then our P is 32 minus 9 or 23, which means that we have how many pages possibly in our memory? 2 to the 23rd, which is the same as how many mega pages? Mega pages, 8 mega pages. See what I'm saying? Because a mega is 2 to the 10th. I'm sorry, 2 to the 20th. So 23rd would be 8 mega pages. Whatever, it's a silly way, that's a silly term that I invented, but the point is 8, what is it? 8 million approximately, whatever. In other words, 2 to the 24th. Or page, 2 to the 23rd pages. You understand that? That this and this have to add up to 32 bits. So if I can figure out this, I know what this is. So that means if I had all the memory available. In other words, if I put in, in a computer, you could buy a 32-bit computer, but not necessarily have 4 gigabytes of memory, which is the maximum. You could have 2 gigabytes of memory. You don't have to have all the memory. But let's say I did have all the memory, I had 4 gigabytes of memory. So then I would take all my memory and divide it into pieces of size 512 bytes. And how many pieces would I have? Like we said, 2 to the 23rd. Of course, I could change this. I could make this 10 bits. Then I'd have kilobyte pages, and I would only have 2 to the 22nd. Or I could change this to 11 bits, and this would be 2 to the 21st. I could keep changing whatever size pages I have. I'll have whatever size pages, the offset will get larger, and then I'll have fewer of them. Right, that's the way it works. If you divide a pizza into 8 slices, then the slices are a certain size. If you divide it into 16 slices, they're smaller.
Yeah, I hate those big ones.
16 slices.
Yeah,
They're just trying to make the woman behind the counter work harder.
it's terrible.
8 slices is
We
reasonable.
can always just cut it ourselves, but.
They don't give you this knife.
I'll make 3 slices.
No.
My kid, when he was very small, he liked to get them divided because then he got more. Then you get 3 slices.
So that's how I always thought.
You get 2 slices that way.
I'd much rather have 2 slices.
Why have 1 slice? Have 2 slices.
It's actually kind of true.
You take this slice and cut it in half. and You get 2 slices. What?
You said that your slice near the 16s?
No, I never would, no, but I would buy like a slice for him and a slice for me, and I have his slice cut in half, and then he'd get 2. And I only had 1.
Oh, yeah.
What?
It's actually less pizza, because you lose some in the cut.
No,
Where does it go?
That's why I always think that getting sliced cheese from the cheese counter is cheaper,
No.
It's not on the knife, you got a roller.
because you don't pay for
no.
they weigh it after they slice it. So you don't pay for the sawdust.
Like the little bit that comes off.
Yeah, you don't pay for that.
Wow.
Gotta think about that.
Over time, that'll adds up to maybe like.
2
$1
shekels.
round.
Like when you see the onions at the store and you turn.
2 shekels, over a month, it could be 2 shekels, yeah.
How much
Okay.
cheese you buying?
Expensive cheese. Okay, I get brie, sliced brie.
Oh.
It's a joke, you can't slice brie. Brie is like cream cheese. Brie is very soft. Sliced cream cheese.
If you try and slice either side of the debris.
Oh, there you go. Okay, so everybody understands the relationship? So that's what this says, M.
Cheese.
By the way, what I said is not just me talking, it's this was M minus N. If N is 10 bytes, 10 bits, then, and this is 32, then the P is M minus N, if M was 32. So for a given logical address space of 2 to the M, like 2 to the 32, the page size is 2 to the N, then the number of pages is 2 to the M minus N. The page table itself will need, this little line here is the byte, is the stinger in the whole equation. The page table itself will need to be in a contiguous location. Because how big will the page table be? Well, theoretically, if we want to enable any program to be able to access any location. And all the memory, let's say, once we have access all the memory, then he'll need to have a row for each possible page. How many pages are there? 2 to the 23rd. How many rows will there be? 2 to the 23rd. He'll have a pretty big page table in the megabytes. The page table itself will be in the megabytes, and every program has its own page table. So we have 100 programs, and they're each using a page table of 2 megabytes. then there'll be 200 MB just wasted on page tables.
So it can't all be 2 to the 23rd.
Well, let's think about it. Let's go to the next picture. Wait a second. Let's go to the picture again. Where is that picture that I like? Here. Well,
There is a suffixal, it's total, all the pages that we have.
right, but let's say my program says, I want to jump to some faraway page. In other words, let's say in my program, I wrote a program that I said, I was in MIPS, right? I was in MIPS. And I wrote a program and I said, I want to make my array, instead of all arrays in MIPS, as far as we remember where they are, but they're 10 million, 10,000, was it something like that?
Yeah.
Right.
Some location like that. Let's say I say that's the beginning of the arrays, but let's say I decide I just love the number 40 million, 10,000. I'm gonna put my array in location, not 40 million, 140 million. I'm gonna put my array anywhere I want. So I put it over there. So from the logical perspective, I have a page with that address set. I'm saying jump to that address and it's my legal address. So I have a page here. So what am I gonna do? I'm gonna say, go to page 453. So now I gotta go to index number 453 in the page table just to find out where that is. So this
You just
page
have
table,
with zeros and blank.
most of the pages in the page table will be blank, will be invalid. That's what
Right.
will be invalid. We mentioned invalid before. Most of the page tables will be invalid, but there'll be one that will be valid way down there. So I don't know. So theoretically, my page table has to be able to access any place in memory.
So the logical.
So, I mean, unless we're gonna say, no, you can only have 4 pages. You know, you can't jump around, but we don't constrain we don't constrain the programmer. The programmer who he's writing in machine language can jump to any place he wants.
No, but why would we?
No, I think that this on the logical memory pages will be numbered 0 to whatever we're using, because look, they don't match up to the physical memory, they're in different orders. So like I think we.
No, but this page number is the index here.
Yeah, but those are both on the side of the program. It's like those don't have any.
No, this is the page table. This is what I said, the 2 megabyte page table, the 8.
Yeah, but that's per program. So we don't care about the actual location memory. Like that's not related to the numbers of the page.
No, right, I could have any number here.
Is on
I could have page number 2000 over here.
No, I mean.
Right, you don't have
This 7 doesn't have to be 7, it could be 7,000.
You don't have problems.
Like I don't see how.
But what if no, but this is the logical program, which means I wrote a program that says jump, and address 10 billion. So I'm now at page 10 billion from a logical perspective. It's true that I'm actually some other location, but I wanted to be able to go there. Now, the program doesn't know what I'm doing. He just knows, take whatever page you're on and use that number as the index into this table. Well, if there is nothing there, if the table is cut short, then how is it going to work? The table has to have a location to be, it's a mapping, because the table is doing the mapping. And if I said, I want to use in my logical memory, I just want to screw up my operating system. So I'm going to use page 0 and page 10 million. So he's got to have a page table that has 0 and 10 million. Now 10 million can't be after page 0 because the way I know where it is by the index.
At that point, isn't it just way better to use like a hash table?
That's what we're talking about. I'm just pointing out what the idea of the system is and the limitations of it. It makes sense so let's say that I have a simple solution. Just make the pages be 10 megabytes. If the pages are 10 megabytes, then if you go back to our picture over here. This is 10 megabytes. How many is 10 megabytes? Megabyte is 20. So 10, well, let's say 10 megabytes, so 8 megabytes. So that'd be 23 bits over here. If I have 23 bits over here, then I'll have 9 bits over here. Now my page tables are much smaller. Right?
Yeah, so your page table would be.
My page table would only be 2 to the 9th, which is a few thousand, like whatever, it's 500 lines. It'll be much smaller. So I can do whatever I want. Of course, what's the problem with that?
Then your pages have.
Well, you can
Your
only.
pages have, this is what Al said, your pages have internal fragmentation. The smallest thing I can allocate to you is 1 page. And it'll be 8 megabytes. So you write a program that says hello world, and it'll sit in memory in 8 megabytes of space. And that's also not great. So you can come up with some compromise. But when computers were small and programs were small, So this was okay, we never got page tables that were too outrageous. Right, you see what I'm saying? It
Yeah.
depends on how big your memory is.
And if your memory changes,
You can always allocate a new page. Wait, so let me continue. So. So here we have a nice, wait a second. Yeah, so here's again that same kind of picture, but you see, we take the P. Here's our 32 bits, and let's say this is 16 and this is 16. So this is 16, so we'll take this page number, and that will be our index into the page table. And that's why I said the page table has to have all possible P's. If there's 2 to the 16th, then it's got to have 2 to the 16th rows, which is a lot, also a lot. Anyway, it'll have all those rows. I'll go to that row and I won't be sitting there. I won't see the number. Let's say he wrote 10 over here. So this is row 10. And row 10, I won't see the number 10. It'll just be that's how I got to there. That's the row, that's the index number. That's why it says a P in parentheses here. This P is saying take this P and it is the distance to travel down. So I immediately jump to that row. And whatever's written here is the F. Why is it called F? The frame number. That's where the physical place is. So if this F is this is 10, let's say this is 20. So now my new address, I'll stick these two things together and I'll put the 20 here and whatever the D was, I'll keep it over here. And if the 20 will be, let's say, F11111, and then the D will be 111, and I'll go to that location. Sorry, in other words, the F will get me to the right frame, and the D will be within the frame, which byte? That's again, the D is the delta. So that's the basic idea. And we can get to the page. So here's that picture we saw a couple times.
the size of our
Where you
physical
see,
memory.
the advantage of this system is that I can have the pages spread out in memory.
The size of our physical memory is always the same, then?
Oh,
I mean, I always have 8 pages.
no, so what about, yeah, it's a good question you're asking. We'll talk about that. Theoretically, could I have, let's say I don't have, let's say logical memory is 32, 2 to the 32. It's a 32-bit machine. The logical memory is 2 to the 32. But I could have less memory. I don't have to, 2 to the 32 is 4 gigabytes. I could have only 1 gigabyte.
Well, then you're fine, but if you go more. You can't
Wait a
have
second,
it.
first I can do either. Now that I've disassociated, I basically, it's like in a car, there's like a gear. And there's like a transmission. Transmission allows the rotation speed of the wheel to be different from the rotation speed of the engine. Right, once they're different, then I can do anything. I could have the wheels going very slow, the engine going very fast. I could do, depending on what gear I put there. So that's we've disassociated the logical memory and the physical memory. They're two different things, and the page table is like the gear that connects the two. And I can do whatever I want. I could have the physical memory be only like 8 pages, and the logical memory be 1,000,000 pages. And when he wants to go to page 1,000,000, I'll just tell him go to page 4, so I can have it be smaller. So that's how you actually would do it. That's how you actually would have a computer that's a 32-bit address, and yet only doesn't have 4 gigabytes of computer. Or today you have a 64-bit address. Nobody has 2 to the 64th memory. That would be a very expensive computer, like in tens and hundreds of thousands. I don't know that much memory. 2 to the 64th is a huge amount. It's very big. It's a gigabyte of gigabytes. It's 4 gigabytes of 4 gigabytes. Anyway, it would be, you don't have a computer that way, so that's how it's done. The actual address that's produced by the compiler is got to be a 64-bit address, but it's going to go to a place that's a low number in that 64-bit, because this is going to always be a low number. The translation is always going to be a low number. I could also make it larger. I could make it larger. It would be a little more complicated. I could make this larger, right? Let's think about that. How would you make it larger? Because any given program can't get to more than 32 bits of memory, right? You can't get more than 2 to the 4 gigabytes. But let's say my computer is 8 gigabytes. So one set of programs can be in the first 4 gigabytes, and the other set can be in the second 4 gigabytes. And as long as my page table can handle it, in other words, my page table can be very long here. The rows can be very long, and I give it a short address, And it changes into a long address, into a longer number of digits, and tells me where to go in the actual physical memory.
Is that a partition then?
I don't have to petition it, no, I'll just say, this particular program. When you give me this address in 32 bits, I'll translate it to this 64-bit address. And now that program will be way down in memory because you went to wherever 64 places you went, wherever you went, I go to wherever I want. Point is, I can have the logical memory could be small, the physical could be larger.
Doesn't have to be together.
They don't have to be together, that's the thing, we've disassociated them.
Right. Like
It's called, right. Here's an example, just if it wasn't clear up till now. Here's my program, A, B, C, D, these are bytes, A, B, C. So where is A? Well, I go to page 0 and it says 5. So I jump down to frame 5, well, frame 5 is gonna be not this one, 1, 0, 1, 2, 3, 4, 5. 20, why 20? Because there's 4 numbers in each one, so 4 times 5 is 20. So we're at page 5, and here's the A. Yofi. Wonderful. Now I want the E. Well, the E is in page 1. So I go to 1 and it says 6. So I go down to 6 and here it is. Now I want the I, or I want the L. So the L is in the 3rd page. I go to the 3rd row here and it says 1. So I go up here to not 0, but to 1, and there's the L. Exactly in the place where it should be. The offset always stays the same. The L is at the end because the L is at the end here. Okay. So here's some nice examples. I like these numbers ones because this is like the overlap between this class and the computer architecture. Calculating internal fragmentation. Let's say the page size is, what is that? That's 2 kilobytes. Process size is 76 bytes, 76 kilobytes, approximately. So how many pages will I need? I'll need 35 pages. So I take 72,766 and divide it by 2,448. Because that's how many pages I need. And that's the size of each page. And I'll get the number 35 and change. What's the change? The change is 100 is that many bytes. You right? You understand? This 2 times 35 is about 70, right? Here's the rest. So how many pages will I actually need?
36.
36, not 35. Because I need one more page for this. So what's my internal fragmentation? Well, it's this, it's the size of a page subtracted by the amount that I'm actually using, 962 bytes. Worst case fragmentation is a whole frame, less 1 byte. On average, fragmentation is half a frame. So the bigger my frame, the more fragmentation I'll have. So small frame sizes should be desirable. But each page table entry takes memory to track. As we said, page sizes grow over time. What he's saying like this is that 20 years ago, the page size might have been 512K. Now it's more like, a megabyte. Now there's or maybe a half a megabyte, maybe whatever, it grows slightly. Still don't want it to be too big, but let's say it's a megabyte. On average, so Solaris supports 2 page sizes, that's what I mentioned to you. So Solaris had an operating system for Unix that had an 8 kilobyte one and a 4 megabyte one, very large page. Process view and physical view of memory, process view and physical memory now very different. Right, the physical memory and the process view of memory is different. By implementation, process can only access its own memory. We've got another advantage, which is that since this page table tells me where to go, no matter what number I come up with, I'm gonna go to look at the page table, and I can only go there. So there's no way for me to get to 12.
So how do we do?
I can never get to 12. Whatever, not 12, this would be 1, 0, 1, 2, 3. Page 3, frame 3, I can never get to.
So how do we use shared memory?
Oh, well, the operating system will give both, shared memory is very easy. I just made my page 12, my page 4 and your page 5 will both go to page 12.
Nice.
That'll be assigned to me. It won't be, it will be my thing. It's just that it'll be also your thing. Okay. So what is this? Free frame list. So here's our free frame list. You see it's 13, 13, 14, 14, 18, 20, and 15. New process comes along and he says, I want 4 pages. So we stick him in and we put him in 0, well, why, I don't know why this is ordered like that, but.
Because of that's the order in the list.
Well, why did we originally assign it? Why didn't we just say put 0? Oh, put 0 and 14,
Yeah.
because it's first in the list, because our list is like a FIFO. So we put it 0 and 14, we put 1 and 13, etc. And now we have a page table. We generated a page table, and here it is. 14, 13, 18, 20. Fine. Now these examples, I don't like these examples from the book because they should have, if I would do it, I would have another, I would have 3 dots and then another box here. Because this makes it look like I make the page table exactly the size that I need. I mean, I could, if I guess I could theoretically. If I knew that it was only 4 pages, then why not make a page that's only 4 pages? But that's not the way we think about it. We think about it as that it's, you just make a page table for the full size, because that's what you don't know. Maybe he'll, even though even though the program itself only needs that, you may, and he needs 4 pages, but you don't know.
I guess you wouldn't want the page table to change, the size of the page table.
I'm just saying, this is a simplistic example. This is saying if the maximum page size is 4, but it's 4 rows, but it's usually gonna be larger. All right. Let's go to the picture and then we'll go back. This is similar to what we saw with caching. It looks similar to that picture, but a little bit different. Here's our address again, right? This is our address. The full thing is our address. This is the page, this is the delta. So really, we just wanted to say here, go to the page table, find the frame, replace the frame, take the delta, and find the place. That was what we saw up to now. Now what are we doing? We're adding another thing called a TLB. Do we have a TLB in the other course? I don't know what it was called. It was something similar, but look-aside buffer. We had a something TLB. Well, this is
Looks
TLB,
like a-
transfer look-aside buffer. This is called the transfer look-aside buffer. Anyway, what this does, it says like this. It says this page is where in memory, which means it's a memory read, which means it's slow. So I don't really want to go there. So what I'll do is I'll make caching, where I said we'll do caching to make it faster. So here's our cache, and we'll call it a TLB.
Translation.
Look-aside buffers. Thank you. Translation look-aside buffer. So what it does is like this. This one has all the possible pages. This one doesn't, because it's a cache, so it's small. So for example, it only has like 8 rows. And what I'll do is like this. These 8 rows could be any of these things here. I'm not going here. I use the P as the index, how far to go down. And therefore, this has to be large enough to take any possible P, which means as many possible P's it could be. I have to be able to go down that far. Here, how am I going to do it with 8? If I use my P as how far to go down, well, I only have 8 rows. I'm never gonna, many times I won't find it. I won't be there. So what we do is we say, no. Well, all these arrows, what it means is we're going to do a simultaneous search, a parallel search. My P could be in any row here. The index is meaningless. The row number is meaningless. My P can go in any place I want. And as long as if I find it, then I know the frame number, and that's my frame number, and I go there. If I don't find it here, it's not in cache. So I've got to go and find it over here, and that'll be slower. And then I'll copy it back into the TLB, and then I'll try to read it, and now I will find it. So I'll always be putting things into cache and maybe removing things from cache. It's very similar. We did almost the exact same thing. But the difference is that there we were talking about,
DMA to go.
no, DMA was something else. DMA was to copy large chunks of memory.
Without going through the processor.
There was a different thing. Anyway, this is basically, it's very similar to what we did there. I can't, it's a little hard for me to remember the other one, but yeah. But if you're reviewing all the time, then maybe you remember.
It's like the fully associated.
Yeah, this cache is fully associated in the sense that any place can be, that's what it means, any place can be to any other place. So now we have what's called a TLB hit or a TLB miss.
Yeah.
And we have that whole thing of hit rate and a miss rate. Because you want things to be in the cache so that you find them. Oh, I think over time so. No?
Yeah.
Yeah. So wait, let me just, all right, so we'll stop here, Yeah, this is a long lecture, this is a.
How many more slides do we
major
have?
topic, and we're not even done with it, we actually have 8, I think, and then 9 also deals with this.
How many more slides do we have this one?
20,
20 more slides?
there were 35 and 55.
We did the major parts that are hard. Here, you wanna, guess which slide is mine? This one. I like to get into very complicated things here, quickly. We'll look at that. Because when you're talking about a 64-bit address,
Yeah.
it starts getting hard to calculate.
Yeah.
But I thought, let's try to conquer that mountain.
Very ambitious.
Why are there dinosaurs on all the slides?
Ah.
And what people say is
There's
that,
old tech.